Hello everybody. In this video we are going to be taking a look at the honors waves and vibrations homework problems 11 through 15. Problem 11. It takes a force of 80.0 newtons to compress the spring of a toy pop gun 0.200 meters to load a 0.180 kilogram ball. With what speed will the ball leave the gun? So let's take a look and see what we are given here. We are given the force acting on the spring is 80.0 newtons. I know that my displacement is going to be negative 0.200 meters, and it doesn't explicitly say that in the problem, but because I know that we are dealing with a force on the spring, we are going to be working with Hooke's law, and I know that that force is a restoring force, so the force and the displacement have to be in opposite directions. So if my force is a positive 80.0 newtons, my displacement has to be negative, has to be in the opposite direction. We're also given the mass of the ball at 0.180 kilograms, and we're being asked to find the velocity. Now you might be saying to yourself, Mr. T, there is no velocity in Hooke's law. What are you doing to me? Again, bear with me. I know I can find the velocity from conservation of energy. Yes, we're going to go back there. And I know in order to use conservation of energy, if I'm going to use elastic potential energy, I'm going to need to know the spring constant. Well, I can find the spring constant because it's not given to me in the problem, but I can find that using Hooke's law. So let's try to do that. I know that Hooke's law tells me that the force on the spring is equal to the negative of the spring constant. Remember, K is my spring constant there, times the displacement. If I want to solve that for the spring constant is going to equal the negative of the force on the spring divided by the displacement. I plug my known values into that. The negative of 80.0 newtons divided by negative 0.200 meters. And again, my two negative signs here will create a positive, is going to give me a spring constant of 4.00 times 10 to the second newtons per meter. Now I know according to conservation of energy, again, we're going to ignore friction, that all of the elastic potential energy that's stored in the spring, once it's released, is going to be converted into kinetic energy of the ball. So I can say that the elastic potential energy is going to equal the kinetic energy. Now we have the initial and final values here, but remember my initial kinetic energy is 0. My final kinetic energy is going to have some value. My initial elastic potential energy is going to have some value, but my final elastic potential energy is going to be 0 because my spring is going to be going to the equilibrium position. So those, the initial kinetic energy and the final elastic potential energy are equal to 0. So we just ignore them in the equation. So I know that my elastic potential energy is going to equal 1/2 kx squared, and my kinetic energy is 1/2 mv squared. I know that these 1/2s are going to cancel each other out, so I have kx squared equals mv squared. To solve that for the velocity, I'm going to have the velocity is going to be equal to the displacement times the square root of the spring constant divided by the mass. I plug my known values into that equation, and I'm going to get a velocity of 9.43 meters per second. Problem 12. What magnitude force will compress a spring so that the spring elastic potential increases by 0.24 joules? The spring constant is 18 newtons per centimeter. So in this case, we are given the elastic potential energy of 0.24 joules. I am given the spring constant of 18 newtons per centimeter. I do need to convert that to newtons per meter. So when I do that, I'm going to have a spring constant of 1800 newtons per meter. And I'm being asked to find the force on the spring. So I'm given the elastic potential energy and the spring constant. I can use my formula for elastic potential energy to find the displacement of the spring. So I know that the elastic potential energy is equal to 1/2 kx squared. Solving that for x, or my displacement, will give me x equals the square root of 2 times the elastic potential energy divided by the spring constant. I plug my values into that equation, and I am given a displacement of 0.016 meters. I can now take that displacement and my spring constant, plug those into Hooke's law to solve for the force. And when I do that, I know the force on the spring is equal to negative kx. Plug my values for the spring constant and displacement into that formula, and I'm going to get a force of negative 29 newtons. And note that because my displacement here is positive, my force ends up being negative because they have to be in opposite directions. Problem 13. A load of 50.0 newtons attached to a spring hanging vertically stretches the spring 5.00 centimeters. The spring is now placed horizontally on a table and stretched 11.0 centimeters. What force is required to stretch the spring by that amount? We are given the force on the spring when it is hanging vertically, and that is 50.0 newtons. I know my vertical displacement is going to be negative 5.00 centimeters, which I do need to convert to meters. That's going to be negative 5.00 times 10 to the second meters. And I know that my displacement in the horizontal direction is going to be negative 11.0 centimeters. And that is going to equal negative 11.0 times 10 to the second meters. Note a couple of things. First of all, I'm using the subscript h to denote my horizontal displacement and the subscript v to denote my vertical displacement, so we don't get those two confused. And I am assigning my displacements in the negative direction. That's just simply so that my forces will end up being positive. I could do it the other way, and that is perfectly fine as well. What we want to find in this problem is the force on the spring in the horizontal direction. In order to know that, I'm going to need to know the spring constant, which I'm not given. But I can use the information in the vertical direction that I have, because I have both the force and the displacement in the vertical direction, use that information to solve for the spring constant, and then use the spring constant to solve for the force in the horizontal direction. Because when I move the spring from its vertical position to a horizontal position, the spring constant doesn't change. That's an inherent property of the spring. So to solve for the spring constant in the vertical direction, I know that the spring constant is going to equal the negative of the force on the spring in the vertical direction divided by my displacement in the vertical direction. And that is going to be the negative of 50 newtons divided by negative 5.00 times 10 to the second minus second meters. And again, my two negatives here will create a positive, and that will give me a spring constant of 1.0 times 10 to the third newtons per meter. I need some good stuff here. That's good stuff. Now I can find the force acting on the spring in the horizontal direction. And I know that that is going to equal the negative of my spring constant times my displacement. So the negative of my spring constant of 1.0 times 10 to the third newtons per meter times my displacement in the horizontal direction at negative 11.0 times 10 to the minus second meters is going to give me a force of 1.10 times 10 to the second newtons. Problem number 14. An aluminum clock pendulum having a period of 1.000 seconds keeps perfect time at 20.00 degrees Celsius. When the pendulum is placed in a room at minus 5.000 degrees Celsius, what is the period? First of all, I can still hear you swearing at me through your computer, so stop that. We know that when the pendulum is in, or the clock is in a room at 20 degrees Celsius, the pendulum keeps perfect time and the period is 1 second down to 3 decimal places. Because the pendulum is made out of aluminum, when we move it into a room at -5 degrees Celsius, because of the temperature change, the pendulum is going to contract. And we know that the period of a pendulum is determined by the length of the pendulum. So when the pendulum contracts, that's going to affect the period. So this now becomes a linear expansion problem. Yes, we are going back that far. So in order to find out how much the pendulum contracts, I need to find the length of the pendulum when it's at 20 degrees Celsius, keeping perfect time. And to do that, I'm going to use my pendulum formula. Solving that for length will give me L equals G times T squared divided by 4 pi squared. I plug in my period of 1.000 seconds, and I'm going to get a length for the pendulum of 0.2481 meters, keeping everything to 4 significant figures. Now that I know the length of the pendulum at 20 degrees Celsius, I can find out how much it contracts when I change the temperature from 20 degrees to -5 degrees. And for that, I am going to need to use my linear expansion formula. I know, another blast from the past. You're welcome. To find the new length of the pendulum using my linear expansion formula, I know that the length is going to be equal to the initial length times my coefficient of linear expansion for aluminum. And because we are talking about length, it is linear expansion. I'll multiply that again by the initial length and multiply that by the change in temperature. So I'm going to plug my known values into this equation. The initial length of the pendulum is 0.2481 meters. My coefficient for linear expansion for aluminum is 25 times 10 to the -6 degrees Celsius to the -1. Multiply that by my initial length and my change in temperature. Remember, change in temperature is the final value minus the initial value. So my final temperature is -5 degrees Celsius. And my initial temperature was 20 degrees Celsius. When I do that math out, I'm going to get a new length for the pendulum of 0.2479 meters, slightly different than the initial length. Now I can take that length and plug it into my pendulum formula to find the new period at -5 degrees. And when I plug my new length of 0.2479 meters into the pendulum formula, the period now becomes 0.9993 seconds. So the period has been altered slightly by changing the temperature of the pendulum. Problem 15. I promise this isn't going to use some arcane formula from 5 months ago. So I'm going easy on you on the last one here. We have an oscillator attached to a rope creates a wave that completes 40.0 vibrations in 30.0 seconds. A crest of the wave travels 425 centimeters along the rope in 10.0 seconds. What is the wavelength? So we are given the number of cycles the rope undergoes, which is 40 cycles. The time it takes to undergo those 40 cycles is 30 seconds. The distance the wave travels is 425 centimeters. I convert that to meters and I have 4.25 meters. And the time it takes to travel that 4.25 meters is 10 seconds. And we are looking for the wavelength. I know in order to find the wavelength, I'm going to need to know both the frequency and the speed of the wave. So I need to calculate both of those before I can find the wavelength. Well, let's start with the frequency. I know the frequency is cycles per second. So there are 40 cycles in 30 seconds. So that is 40 divided by 30 is going to give me a frequency of 1.33 hertz. Now, one thing people have a lot of questions about with frequency and period is knowing when to put the number of cycles in the numerator and the seconds in the denominator or vice versa. Remember, frequency is measured in hertz, and hertz is equal to seconds to the minus 1, or 1 over seconds. So whenever I'm dealing with frequency, I always want my time value in the denominator. To find the speed of the wave, I can just simply take the distance it travels and divide it by the time it takes to travel that distance. So 4.25 meters divided by 10.0 seconds is going to give me a wave speed of 0.425 meters per second. Now I know my frequency and my wave speed, I can calculate the wavelength. And using my wave speed formula, V equals F times lambda. Solving that for lambda, I'm going to have lambda equals V divided by F. I plug in my values for wave speed and frequency, and I am given a wavelength of 0.320 meters.